Good morning, my dear students. Welcome to class 4.1. We are studying about introduction to nanostructures, and we have seen some different nanostructures. And today we are going to talk about quantum dots and semiconductor and magnetic nanoparticles and their biomedical applications. So that's where we are looking at a new area of nanostructures and their applications. And this is for course number PHA 6146, and I am your professor Yashwant Pathak. So the learning objectives of this class are to understand quantum dots and semiconductor nanoparticles, describe the quantum confinement and quantum dots, describe fabrication of quantum dots, identify quantum dot applications, and describe magnetic nanoparticles and their biomedical applications. So these are some of the learning objectives we'll be studying in this particular class. So quantum dots are semiconductor nanocrystals that exhibit unique optical and electronic properties due to quantum confinement. We already have seen in details about the nanocrystals, and there we were discussing that nanocrystals have a lot of properties which are very useful in semiconductors and in medical applications also. So their size and composition can be engineered to control the color of light they emit and making them useful in various applications including displays, bioimaging, and solar cells. We already have seen that in the daylight you get some wonderful displays because of the nanocrystals which are inside the display. Mostly you will see them around the highways and in downtowns or in Times Square also. So a semiconductor is a material with electrical conductivity between that of a conductor and insulator, and commonly used in electronic components like transistors and integrated circuits. These materials such as silicon are crucial for medical technologies also, enabling the functionality of smartphones and many other devices which are very useful for the human life. So quantum dots are semiconductors whose excitons are confined in all three dimensions of space, and quantum dots have properties combined with those of bulk semiconductors, those of atoms, and different methods to create quantum dots and medical applications. These are some of the things we are going to see very soon. And based on your particle size, the properties of these quantum dots change, and it is very interesting to see how these things happen. So thin film semiconductors are electrons in conduction band, and holes in the valence band are free to move in two dimensions. So either they can go in EC or EV dimension quantum dot, and confined to one dimension by a potential well. So potential well created due to a larger band gap of the semiconductors on either side of the thin film. And thinner films lead to higher energy level. So you'll find that when you want to have displays, thinner the better, because then you have higher energy level there, and that is what you are seeing in our new quantum TVs also. They are known as quantum TVs because they are using these quantum dots inside the TV tubes, and that's where you get higher energy level and better pictures also. And thin film semiconductors are semiconductor material deposited as very thin layers and typically onto a substance like glass or silicon. And these films are crucial components in various electronic devices, from transistors, photobodies to solar cells and displays. They are essential for modern technology, powering everything from smartphones to computers to car and aeroplanes. So you can see the application of quantum dots is versatile. It can be utilized in many different ways, and this is a typical picture you can see here is conduction band and the valence band, and in between there is a gap, and this gap, this creates a lot of energy here, and it all depends upon the between distances between these two. So thinner the layer, better the higher energy levels, and that leads to better pictures and better displays and better even smartphones. You will find that smartphone 1 or 2 iPhones where using some of this technology, but over the period of time the technology has improved, and you will see significant improvement in your i16 and i15 smartphones or iPhones there. So quantum wire is another possibility, that either it is a dot or quantum wire. So thin semiconductor wire surrounded by a material with a larger band gap, and surrounding material confines electrons and the holes in 2 dimensions. Carriers can only move in 1 dimension due to the larger band gap, and quantum wires acts as a potential well. Quantum wires are extremely narrow structures where electron transport is possible only in a very few transverse modes with energies less than the Fermi energy, and quantum wires can be used as electron waveguides. Semiconductor quantum wires have been used to make switchable high-speed lasers, and quantum wires can be fabricated by an appropriate arrangement of metallic gates on top of 2D electron gas. And this is where this advantage of the quantum wires are there, and they are widely used now in electronics mostly. So quantum dots, electrons and holes are confined in all 3 dimensions of space by a surrounding material with a larger band gap, discrete energy levels, artificial atoms, and a quantum dot has a larger band gap, and like bulk semiconductor, electrons tend to make transition near the edges of the band gap and in quantum dots. And this is where you can see all these changes happening, bulk, quantum well, quantum wire, and quantum dot, the movement of the electrons happening in the system. So quantum dots are very small semiconductor particles with a size comparable to Bohr's radius of the excitons, and separation of electron and hole. So typical dimensions are 1 to 10 nanometers. So they are very, very small, almost atomic level, close to atomic level, and can be as large as several micrometers also. So you can move, and based on how they are particle sized, their properties change. So if you see that core size is 2 nanometers, then normally it will have 15 items. If it is 3 nanometers, it is 30 items. If it is 4 nanometers, it will have 50 atoms. If 5 nanometers, it is 80 atoms, and 7 nanometers, it will have 150 atoms. And number of active centers will also be changing there. And this is where the properties will also change. So you get it in the different sizes and shapes like cubes, spheres, pyramids. Key properties and characteristics of quantum dots are their properties are size dependent. So 1 nanometer, 2 nanometer, 4 nanometer, 7 nanometer, the sizes are different, and if it is in micrometer, then their properties are also different. So their electronic and optical properties are dictated by their size rather than their bulk material properties. So obviously bulk material might be anything, but then when it comes down to the very low sizes, their electronic and optical properties become very specific for the specific size. Second thing is tunable emission. By controlling the size of the quantum dots, researchers can tune the wavelength of the light it emits, and allowing for the creation of specific colors. So you can manipulate the sizes, and you can the emission or the kind of wavelength it can emit can be controlled with the help of tunable emission. And then there is a high brightness and photostability. That's what I was pointing it out, that when there are displays, now you can see them very clearly in daytime in the sunlight, and that is where this brightness and displays is coming up based on the properties of their emission properties of these nanocrystals or semiconductor quantum dots. So quantum dots can be highly efficient at converting light energy into specific color and are more stable than traditional fluorescent dyes, and meaning they don't degrade as quickly when exposed to the light, and this is the advantage of these nanocrystals, nano quantum dots. So discrete energy level, the energy level depend on the size and also the shape and the quantum dot. Quantum dots exhibit discrete and quantized energy level due to quantum confinement and phenomenon where electrons are trapped within the small space, similar to how electrons are confined in atoms. This confinement leads to energy levels that are separated and distinct rather than the continuous as in bulk material. The energy level spacing can be tuned by varying the size and composition of the quantum dot. So you will find that the energy quantum changes with the particle size distribution. So if you have what type of diameter of the bulk material, and then you come down to the quantum dots and then the size of the in nanometers, so that will decide how the discrete energy levels are changing. So you see a conduction band and valence bond here, but gradually they get separated and they exhibit different properties. So smaller quantum dots, higher energy required to confine excitons to a smaller volume. Energy levels increase in energy and spread out more. Higher band gap energies are there. So this is the advantages of these quantum dots, and you can utilize them for appropriate emissions of the colors, and then you can have beautiful displays there. And same technology is used in now the TVs, the new TVs known as quantum TVs. So CDSC, this is cadmium and selenium quantum dot. 5 nanometer dots are red, while 1.5 nanometer dots becomes violet. So this is 5 nanometer, this is 1.5 nanometer. So if you use the combinations of this, your display can have different colors, different particle sizes are there, and you can the displays can have different colors, and they show it very well. And this is very interesting advantage of these quantum dots. So how to make the quantum dots is quantum dots can be synthesized using either top-down or bottom-up approach. Bottom-up methods are like colloidal synthesis are common and involving growing quantum dots from smaller components in a solution. So you take atomic solution, the particles are in the atomic level or even smaller than that, and then gradually let them grow under controlled condition to a desired particle size. So from 1 nanometer you can get into 10 nanometers from the atom, because the normal atoms are around 1 nanometer. So what you do is you use the potato, they call it, but the atomic stage type of solutions, and then deionized water is added, and then you extract use the filter, extract the potatoes, then cadmium sulfate are added there, and titanium is also added, and finally you can make a combination. Electronic steam pressure sterilizers are used to convert them into quantum dots in aqueous solution. So this is a technology which is used for creating the synthesis or synthesizing the quantum dot. It appears to be very simple, but when you do it, it has several controlled features. You need to control so many factors here to get the desired quantum dots. So another method is hydrothermal synthesis. Is cost effective and suitable for mass production. Electrochemical methods can also be used to create quantum dots. There are three main ways to confine excitons in semiconductors, either using lithography or using colloidal synthesis or using epitaxy, and you can get pattern growth or self-organized growth. So these are some of the advantages of different techniques which are used. So lithography, quantum wells are covered with polymer mask and exposed to an electron or ion beam, and the surface is covered with a thin layer of metal, then cleaned, and only then exposed areas keep the metal layer. So pillars are etched into the entire surface, and multiple layers are applied this way to build up the properties and size wanted. But the disadvantage for this method is it is slow, there is a possibility of contamination, low density, and it can defective formation of the system. So you have here polymer mask, electron beams, and then it can go with provide the active ions, and finally you can get some quantum dots at the end of the processing, lithographic processing. So but it has, as mentioned, it has definitely some disadvantages, like it is very slow process. There is a possibility of contamination during the process. If contamination happens, then all the properties will be changed. Low density and defective formations are some of the challenges. In case of colloidal synthesis, immersion of semiconductor microcrystals in glass electric matrices and taking a silicate glass with 1% semiconducting phase like cadmium sulfide or copper chloride or cadmium selenium or copper bromine. So these are some of the possible elements which you use, or they are rather combination of the elements, and heating up for several hours at high temperature. Formation of microcrystals of nearly equal size can happen. Typically group 2 to 4 materials, CDS, CDAC, and size variation, size dispersions vary. So you need to have a very controlled environment where you can get a desired size of nanoparticles, and that is the key for colloidal synthesis. Epitaxy is a pattern growth where semiconducting compounds with smaller band gap GAAs are grown on the surface of compound with a larger band gap AlGAs, and growth is restricted by coating it with the masking compounds like silicon dioxide and etching that mask with the shape of the required crystal cell wall shape. So this is a typical picture, and you can see this is 0.5 micrometers, and then from there you can come to 1.5 micrometers, and you can play with these things, and finally you can get around 5 micrometers dots. And disadvantage is density of quantum dots limited by mask patterns. So how mask patterns are used, so you can go further down to the nanometer levels also using the epitaxy pattern growth. So epitaxy self-organized growth is another way where it uses a large difference in the lattice constants of the substrate and the crystallizing material. When the crystallized layer is thicker than the critical thickness, there is a strong strain on the layers, and the breakdown results in randomly distributed islets of regular shape and size. And this is where you can find this picture which shows the substrates and forming the quantum dots on the top of that. Disadvantage here is size and shape fluctuations. It varies based on how the control conditions are followed, and then the ordering of the system is can vary with the processes. Then there is cadmium free quantum dots, like CFQD. In many regions of the world, there is now or soon to be legislation to restrict and in some cases ban heavy metals in many household appliances such as IT and telecommunication equipment, lighting equipment, electrical and electronic goods, toys, leisure, sports equipment. Now you can see that this cadmium free quantum dots, they want to find out they want to remove these heavy metals from the major preparation of the quantum dot, because they are finding that if they are in the household appliances, then they affect the health of the people, and that's why they are trying to ban these quantum dots with cadmium and other heavy metal, because it may be detrimental to the health care of the people who are using them. So quantum dots, to be commercially viable in many applications, they must not contain cadmium or other restricted elements like mercury, lead or chromium. And research has been able to create non-toxic quantum dots using silicon. So now major focus is on silicon, because all other heavy metals like mercury, lead, chromium, cadmium can create healthcare problems for the users if they are part of the household appliances. So what is it good for? So very narrow spectral line width depending on the quantum dot size. You can see different colors here. Multiplex detection, large absorption coefficient across the wide spectral range, small size and high surface to volume ratio, and very high levels of brightness and blinking. So these are some of the advantages of these quantum dot semiconductors. So applications are in photovoltaic devices, solar cells. Biology is biosensors and imaging, which is used for cancer detections and some problems in the body or organs in the body. Light emitting diodes, which is LED bulbs and all those things they can use. You can see such a beautiful, colorful display. You can find it out in your systems. Then quantum computation is there. In computer, they can be nanocrystals, quantum dots can be used. Flat panel displays like TV and all those things, or on the commercial displays which are available across by the side of the roads. They use these things. memory element, photo detectors, and laser. These are some of the applications. You can see here the laser beams which are coming out of the nanocrystals and very useful in many different equipment. They are useful in your analytical equipment also, laser beam, but they are very expensive, as we have already seen in our previous class. So biomedical applications of carbon quantum dots they are used in bioimaging. They are photodynamic and photothermal therapy. Two-dimensional quantum dots are for biological application. Gene delivery, you can use quantum dot, as well as targeted drug delivery. So now probably you are comfortable with the concept of targeted drug delivery, where the drug carriers, they straightway go to the desired place in body or organ in body or a tumor in body and deliver the drug there. That is targeted drug delivery. While when you use the genes or genetic structure like DNA, mRNA, siRNA, all these are also delivered using these quantum dots. And then bioimaging is, MRI, all this magnetic resonance imaging, all this, they try to use quantum dots and get much better pictures of the internal parts of the body, and you can detect the diseases at an early stage using these things. And then photodynamic and photothermal therapy, where you can put the drug into the carriers, quantum dots, and then they go there, and then at some point with the temperature changes in the body, the drug can be released, and that is called photothermal therapy or photodynamic therapy, and that is where the quantum dots are widely used. So carbon quantum dots are applied in various applications in biomedical fields such as gene delivery, genotyping, electrochemical biosensing, pharmaceutical formulation, photodynamic and photothermal therapy, cancer treatment, bacterial infections, and inflammation due to aforementioned, reduction of oxygen that creates ROS, reduced oxygen species, and that causes lot of inflammation, and that's where this can be used. So carbon quantum dots are low toxicity, reasonable good water solubility, and chemically inert, blinking and excitation dependent PLA emission is also possible there. So these are some interesting applications of biomedical applications of carbon quantum dot, which are also used in semiconductors. So solar cells is another area where this is widely used, and they are known as photovoltaic cells. P and N junctions are there, and this is how these electrons are distributed, and you can see the P type and N type, two different types are there, and depletion layer with if they combine together, then you see a electrical field in between, and that's where your can be used for solar cells, this technology. And sunlight excites electrons and creates electron hole pairs, and electrons concentrate on one side of the cell and holes on the other sides, and connecting the two sides creates electricity, and this is where the electric field is created, and then you can save the electricity or preserve or store the electricity from the solar cells, and this is where the simple technology they are adopting. So different generations of solar cells are there. Are 4 different generations nowadays. Earlier it used to be 3, and now they have added one more generation, which is 4th generation. So first generation is single crystal silicon wafers. Advantages: high carrier mobility. Disadvantages are most of the photon energy is wasted as heat and expensive. So that was your single cell silicon wafer. In good old days it was there. So gradually they improved the technology and brought thin film technology. This is less expensive but efficiency lower compared with silicon solar cells. Then the 3rd generation came, where now they are using nanocrystal solar cells, which are quantum dot nanocrystal solar cells, and this enhances the electrical performance of the 2nd generation while maintaining low production costs. So now you will find that gradually from 1st generation to 3rd generation, the cost of the solar cell is going significantly down, and I am sure it will be within the reach of average people, and they can utilize this and they can reduce their electrical bills. And 4th generation now is the generation focuses on combining the flexibility and low cost of thin films with the durability of inorganic nanostructures. So now they are looking at using inorganic quantum dots for these or nanostructure in the thin films, and that way they can improve the efficiency of the solar cells, and that is considered to be the fourth generation. And I am very sure in coming few years you will have better few more generation, because as we have seen in our previous class that now they are coming up with solar paints, so you can just paint the whole of your roof, and once you put it, those solar paints can convert the solar energy into the energy which can be used into as a electrical energy, and now you don't need the solar cell, you just have solar paint to do that, and that might be probably fifth or sixth generation. We are waiting for that to come and in the market. So solar cells efficiency is different for different generations. So from 1975 to 2010, you'll find that efficiency has grown from 12.1% to 40.7%. And this is what the researchers in the solar energy is going on. Mostly it is the chemical engineering department which works. We have a wonderful solar energy center in College of Engineering at USF. But what limit the efficiency is photons with lower energy than the band gap are not absorbed, and photons with greater energy than the band gap are absorbed, but the excess of energy is lost as heat. So now they are trying to find out how this heat created during the process can be converted to electricity, and that is where the new generations will come into the picture. But you can see how universities have contributed there. Some of the names of the universities are here, and they are doing a phenomenal work here, and this is very helpful to understand how these quantum dots are changing the solar energy efficiency. So how quantum dot improve the efficiency? The quantum dot band gap is tunable and can be used to create intermediate band gaps, and the maximum theoretical efficiency of the solar cell is as high as 63% with this method. So now they are improving it. So from 42 now they are reaching almost 62% if you use the quantum dots, and this is where the simple pictures are here to understand. So what is biological imaging of nanocrystals or quantum dots? This is a typical picture of the cells, and you will find that these quantum dots are inside the cell and they are producing fluorescence. So you can look at your cells and the how these quantum dots can enter inside the cell, and you can look at them under the microscope. And this picture shows silicon quantum dots fluorescing inside the cancer cell, and you can identify where they are and how they are and what are the tumor strength, and gradually you can find out some treatments for this using that imaging. And this is typical bioimaging. They are using this quantum dot. So here you have 0.5 micron, 10 micron, 5 micron, and in rat body also you can see this quantum dots in cells, and you can find the fluorescence of those. So they have, they use wide field confocal microscope for these purposes, and then they can fluorescence is created using different types of nanocrystals, and you get a spatial resolution as well as temporal resolution, and you can learn more and more about the cancer cells and at what stage the cancer is. And this imaging is very important applications of the quantum dot. So it is also useful in the targeted drug delivery. So we attach drug molecule to the quantum dots, which will then be able to deliver the drug just to the cancer cells where it is needed and not to the whole body, because they are all the cancer drugs are normally poisonous in nature, so they can kill the cancer cells as well as the good cells also, and you don't want that to happen in the body, and that is where this targeted drug delivery helps you. So you have this quantum dot, and then you attach the targeting molecule and you attach a drug here. Now this is a anti-cancer drug. Now they come into the body and then they enter in the cancer cells, and then they release the drug, and when the drug is released, then the drug can interact with the cells of cancer or cancer cells, and they kill the cytoplasm and kill the cancer cell there. So current anti-cancer drugs tend to have a range of unpleasant side effects because they are poisonous in nature, because they affect the whole body and not just the cancer. And this targeting of the molecules will prevent the destruction of the cells of the whole body, but focus only on the cancer cells inside the body. And I'll recommend you to read this nice paper on quantum dot based targeted drug delivery system. It will give you a lot of inside understanding this. Then light emitting diodes, LEDs, they can use this quantum cells. So quantum dots, which are nanocrystal that can emit light of specific colors when excited, and when incorporated into LEDs, they enhance the color purity, brightness, efficiency, leading to improved display and lighting technologies. And quantum dots are semiconductor nanocrystal, typically a few nanometers in size, exhibiting unique quantum mechanical properties and their ability to emit light of specific colors. So this is QEDs, the LEDs, which is light emitting diodes. These are all nanocrystal, and now you will find, as I mentioned earlier also, that when they used to use tungsten wires in the bulb, they used to get off 3 months or 6 months, maximum 1 year. Now the LEDs can continue for a long time, and the life is also prolonged. And smaller quantum dots emit shorter wavelength blue light, or while larger quantum dots emit like red light. So you can get different types of lights from the. Nowadays you will find that new fans which come with the LED lights, you can change the colors of the lights also, and that is a advantage of these nanocrystals which are used in household lighting system. Now there is another interesting application, is called anti-counterfeiting. And anti-counterfeiting refers to various strategies and technologies used to prevent the production and sale of counterfeit goods. It involves a combination of measures to protect consumers, brand, and rights of owners from the harmful effects of counterfeit. So you can see this if you look at under the magnifying glass, you will find that this is a counterfeit dollar bill, and that's where you can identify and you can check it out. So from consumer goods like music, software, to critical products like drug shipment and even currency itself, quantum dots provide a method of creating unique optical barcodes. So nowadays these quantum dots are included into your dollar bills, and you can, they protect from counterfeiting, and that's very interesting application of quantum dot there. And they have optical barcodes, the precise combination of wavelengths of light emitted by complex combinations of different quantum dots in the system. And embedded in inks, plastic, glass, or polymers, quantum dots are invisible to the naked eye and impossible to counterfeit. So basically what they are doing, when they print the dollar bills, they will incorporate certain specific nanocrystals in the ink, and now once they are incorporated on the dollar bill, you cannot get a counterfeit dollar bills, because they cannot be replicated by the people who do these counterfeiting businesses. So sensors is another area where these quantum dots are used, and the properties of quantum dots are such that they can be functional to emit light on binding to target molecules, which enable them to be used, for example, to detect specific airborne pollutants. So this is another application of that. Quantum dots are used in sensors to detect various analyses by leveraging their unique optical properties. Quantum dots can act as fluorescent tags, intensing sensors and components in energy transfer based on sensing systems. So the quantum dot, because of their very small size and optical properties, can be utilized for different types of applications and using as part of the sensors. So some of these quantum dots are also used in cars, and they will know that they show it. You have a cameras nowadays, eyesight camera they call it, and they use these quantum dots to exactly pick up the cars which are running by you, and they immediately tell you that, hey, don't change the lane. This is the advantage of these sensors, which are now part of our life. It has really influenced our life significantly and made our life safe also. And then their tunable emission and high surface area enable sensitive selective detection in applications ranging from medical diagnostic to environmental monitoring. Nowadays, we get a lot of data on the environmental pollution, and this environmental pollution can be measured using such type of sensors which carry the nanocrystals or quantum dots, and we get pretty close to accuracy environmental data or environmental parameters. Quantum dots can be used in image sensor founding in cameras and smartphones to improve light absorption, dynamic range, and especially in low light conditions. You will find that now the newer cell phones can take pictures nicely in the dark also. This is where these quantum dots are helping us, and it's a great application and improving the technologies electronic technology also significantly, and it can be used as gas sensor and biosensor. So some of these applications are shown in this picture, which shows energy storage, biosensing, biomedicine, and energy harvesting. These are some of the applications of the quantum dot sensors. So conclusion is that quantum dots are semiconductor particles with a size in order of Bohr radius of the excitons. Energy level depend on the size of the dots. Different methods for fabricating quantum dots are lithography, colloidal synthesis, epitaxy, and it has got several multiple applications, and that's why quantum dots are a very important part of the nanotechnology, nanostructures. So now we'll go for the second part of this, which is magnetic nanoparticles and their biomedical applications. So this is magnetic nanoparticles are referred to nanoparticles made of magnetic material. They are referred as magnetic nanoparticles, and these particles can be moved by applying magnetic field. So you can use some external field to move the particles inside the body also, or in any system where you want to use them. And these particles can be moved by applying magnetic fields, which allow them to be controlled inside the body. So if you have magnetic particles, they can reach the typical cancer cells, and then you can manipulate from external magnetic pressure force, and then you can ask the magnetic, you can get the drug released from these magnetic particles. And this is where the technology is moving, and it's very interesting. Especially nowadays, majority of this technology is used in cancer patient, but gradually it will go in different organs also. So magnetic nanoparticles suspended in solution are called ferrofluids, and have many applications in medicine, acoustics, and electronics. So iron oxide, very stable and easy to synthesize, biocompatible, minimally toxic, used in many clinical studies. FDA approved for some application, mostly in cancer. Reasonably large saturation magnetization can happen, and the most widely investigated types are magnetic nanoparticles for biomedical application. These are the pictures of the nanoparticles which are used in the biomedical application. They are magnetic in nature. So you can attach your drug to nanoparticle and attach a targeted moiety which can take these nanoparticle, magnetic nanoparticle, to the tumor cells, and then you excite those nanoparticles, and the magnetic nanoparticles will get excited. Once that excitement happens, it will release the drug, and the drug will act on the cancer cells but not on any other cells in the body, and that is the advantage of this magnetic nanoparticle. So surfactant magnetic nanoparticles can stick together if they collide, and this can be lead to agglomeration, which is generally detrimental for application, because then you have high number of nanoparticles which can be carrying the drug, and then suddenly they burst out, and then it might affect your body very badly, adversely. And that's why they use different types of surfactants, which are known as organic surfactants, normally long chain molecules including fatty acid, dextrans, alginate, and other polymers, or inorganic surfactants, which are non or weakly reactive materials like silicon dioxide, AU, or others. And core shell nanoparticle structures can also have different types of functionalities. You can have quantum dot, and surfactants can also introduce additional binding sites to the magnetic nanoparticles, and you can attach more thing. To add two or more drugs also can be attached to the nanoparticles if you use some of these surfactants on the surface. So challenges with nanoparticle, here is a very nice picture which shows magnetic nanoparticle application. They are used in external magnetic field. So this is your cell, the particle gets into it, and then you excite it from the magnetism outside, magnetic field, and then it can release the drug. So you will see magnetic hyperthermia therapy. So it can increase the temperature, and the increased temperature can also, in the normal magnetic nanoparticles, when it comes to the body temperature, if the temperature is 37 degrees centigrade, then they may release the drug because of the hyperthermia therapy. Drug and gene delivery, it can be used. It can be used for MRI contrast. You can see what is happening in the brain. And then magnetic bioseparation can also be seen in the system. So some of these drugs are separated from the nanomagnetic particles. So magnetic nanoparticles have diverse biomedical applications, including magnetic resonance imaging, MRI, targeted drug delivery, hyperthermia, biosensing, and their unique magnetic properties combined with the ability to be functionalized. You can add different types of functions, attaching some moieties there, attaching some linkings, and that helps. That is called functionality of the nanoparticle. And combined with ability to be functionalized with various molecules, make them ideal for both diagnostic and therapeutic purposes. So you can attach some fluorescent materials to this, and then you can get use them for diagnostic purposes, or you can attach different types of drugs to this with the surfactants included, and then the drug can be delivered. So at a time you can have multi-drug therapy for cancer cells, and that is possible using this magnetic nanoparticle. To be used for biomedical application, magnetic nanoparticle must be injected into body. For many proposed applications, this injection would be done intravenously, which requires a good understanding of the hydrodynamic response of the nanoparticle. So now in this scenario, what you want is your nanoparticle should be targeted, and then they can be injected. So they should be very small, it's 1 to 100 nanometers. So they are smaller than the RBCs, smaller than the red blood cells or white blood cells. So they circulate into the systemic circulation, and the attached targeted moiety will take them to the cancer cells, and this is how it works. So because of their small size, magnetic nanoparticles often exhibit complicated hydrodynamic properties when suspended in solution, and fortunately the problem understanding small particle in solution was solved by Einstein many years ago. Einstein had helped in understanding this thing almost a century back. And since magnetic nanoparticles are sensitive to magnetic fields, applied fields can produce additional magneto-hydrodynamic effects that are absent in non-magnetic nanoparticles. So you can manipulate from the external forces there. And furthermore, since nanoparticles will often functionalize by attaching surfactant, it is also necessary to understand how these surfactants will affect the hydrodynamic responses. And I will recommend you to read this article, which is published in MDPI, and it is a very nice article which gives you more insight into the magnetic nanoparticle application. So principle of local chemotherapy with magnetic drugs targeting is, you have external magnetic field gradient will produce a force on magnetic nanoparticle. There is a considerable interest in using this effect for targeted drug delivery by attaching the drug to the magnetic nanoparticle, then applying a large magnetic field to the desired region, a cancerous tumor or damaged joint, which will attract the magnetic nanoparticles, hence also attract the attached drug too. And then this illustrates one of the recurring themes of many possible biomedical applications of magnetic nanoparticle. It is believed to be safe to apply relatively large static demagnetic fields to the patient. So they can apply the static magnetic fields around the human body, and then they will play with this movement of the magnetic nanoparticle inside the body. So you can, when you inject it, it's here. Now this is interesting picture here. So mitoxantron coupled with ferrofluid, these magnetic nanoparticles are injected into the artery, and from artery it will go to the tumor, and from tumor, when you use pole shoe of the magnet, then this external force will create some vibrations in the magnetic nanoparticles, and this drug mitoxantron can be released inside the tumor cell. So it is not affecting any other cell, but it directly gets into the tumor cells using the normally they use antibodies for these purposes, and that's where the field gradient can change. How much drug you want to release will be depending on what type of magnetic field you are applying near the body, and that's where you can control the release of the drug also. So this application requires attaching the drug to magnetic nanoparticle without strongly deteriorating the magnetic response of the composite and efficacy of the drug. And detailed hydrodynamic modeling is difficult. This, people are still exploring. So there is a lot of research needed in this area. The magnetic localization is expected to require very large field gradient in the order of tens of T per meter for even relatively low blood flow rates and large magnetic nanoparticles. So this is a schematic description of how these ferrofluid or magnetic nanoparticles are injected, go in artery. From artery they go to directed to the cancer cell, and from there they excite the magnetic nanoparticles and release the drug that is in the tumor. So iron cross-link number of particles. So you can see this picture. This is a scanning electron microscopy with 500 nanometers is this big. So these are all around 100 nanometer particles, and they can be seen. And you can see the excitement which happens applying external pressures, and you can release the drug in the system. So calcium 2-valence, cross-link with nanoparticle, they look like this in under the TEM, and you will see 20 nanometers here. So you can see several particles within 20 nanometers. So the particle size must be like 1 to 5 nanometers there in this cross-linking. So magnetic hyperthermia is another area which is used, and there are several therapeutic benefits in producing localized heating. For example, delivering the toxic doses of thermal energy to tumors or increasing the efficacy of certain anti-cancer drugs. However, heating the surrounding tissue can also produce unwelcome side effects. So when you use this hyperthermia technology, magnetic hyperthermia, it can also affect the surrounding tissues also. So it will all depend upon how big is the tumor, because if the tumor is 1 millimeter, 2 millimeter to few centimeters, probably it will have very different effects. So it will all depend upon what size of the tumor is there, and how this hyperthermia can be utilized. So heating the surrounding and treating cancer tumor, the general measure of effectiveness is the cumulative equivalent minutes at 43 degrees centigrade. So normal body temperature is 37 degrees centigrade. Now you can create a temperature of around 43 degrees centigrade using magnetic hyperthermia, and that can be helping the drug to effectively work therapeutically. The magnetic moment on nanoparticle will align with the external magnetic field, and as the external field changes direction, the magnetic moment will also change direction, and this produces dissipation leading to heating. So if you apply the two magnets from two different sides of the body and where the tumor is, and then you change the directions, it will create a energy dissipation, and high energy will be created, and that will create hyperthermia. One of the major advantages of using magnetic field to produce heating is that they readily penetrate the tissues. That is the advantage of it. So here some of the pictures will show you thermal cancer therapy, nanoparticle in the field 3 points, magnetic nanoparticle, polymer coating, heat generation, and then the drug is released inside the cell. So these are some of the areas which are applicable. They use magnetic hyperthermia application. So relaxation in magnetic nanoparticles can be applied. There is a Brownian movement. All fine particles, finer than in the nanometer scale, they are continuously moving because they have high energy. That is called Brownian movement of the particles, and Brownian relaxation is also part of it, that they will move and they relax, they will move and relax, and this is how the movement happens, and then it goes back to the thing. So there are two types of thing. One is nil relaxation is there, which is nanoparticle remains fixed in place, but the magnetic nano movement reverses direction to align the external field. That is known as nil relaxation. So practical aspects of magnetic hyperthermia are: magnetic hyperthermia requires large magnetic fields alternating in high frequencies to be effective. In practice, it is challenging to meet these two requirements simultaneously. The circuit diagrams on the left shows one approach to designing apparatus suitable for hyperthermia. This particular system provides a field of just over 0.01 T at a frequency of almost 400 kilohertz. And high currents required for producing high magnetic field leads to substantial resistive losses, and therefore significant radiative heating is there, and this can be minimized. To avoid heating the entire sample can be done using water cooling systems and all those things, but it is still experimental. People are learning more and more to find out how it can be utilized. So magnetic hyperthermia is sample consisting of individual nanoparticles heats 4 to 5 times faster than the sample with clustered nanoparticles. So individual nanoparticles are much better than the clustered nanoparticles. That's what they found it out and reported. This suggests that at least for these experimental conditions, nanoparticle size, driving frequency, sample, viscosity, etc., Brownian relaxation is much more effective heating than mechanism in nil relaxation. So these two relaxation, either Brownian movement or nil relaxation, nil relaxation provides a better Brownian relaxation is much more effective than the nil relaxation when it comes to magnetic hyperthermia. So concentration dependence of magnetic heating is you can have here that different magnetic concentration they are using 25 milligram, 50 milligram, 25 milligram, and you will find that this relationship is very different with the system. So this is your buffer, and as you add more and more of the nanoparticles per milliliters, the effects are different. So higher concentration of magnetic nanoparticles will lead to greater amount of heating during the magnetic hypothermia. So this is where you are getting 100 milligram per ml and high amount of energy is created and leading to hypothermia. However, increasing the concentration of nanoparticles may lead to increased toxicity and other undesirable effects. That is the challenge there. So you cannot just use, but you have to find out the benefits and losses and make your decision. So understanding the heat flow from magnetic nanoparticles into surrounding tissues and then through surrounding tissues will be important when designing specific application. And this is again I have mentioned, it's in experimental stages and working on it. So magnetic relaxation describes how a magnetic system returns to its equilibrium state after being disturbed by the external magnetic field. So Brownian movement and nil relaxation, these are happening because of the external magnetic forces which are applied, and this process involves the magnetic moments within the system changing orientation and aligning with the applied field and relaxing back to their initial random orientations when the field is removed. It is characterized by relaxation times which indicate how long it takes for the system to return to the equilibrium, because that is normal natural equilibrium status. They want to go back. When you excite the magnetic nanoparticles and remove the external magnet, then they will try to go back to the relaxation mode or relax system, and that's where they change. The properties are different in both Brownian or nil relaxations. So T1 is longitudinal relaxation time, while T2 is transverse relaxation time, and T1 is a measure of how long the magnetization takes to recover to align along with B after being flipped 90 degrees. This depends on interactions for the moment with the other particles and referred to as spin lattice relaxation. Or T2 is a measure of how long spins will rotate together with the flip 90 degrees. This is affected by the depression rate, which depends on local magnetic environment, and T2 relaxation depends on the interaction of moments with the magnetic field. This is referred to as spin-spin relaxation, and different types of tissues have different T1 and T2 relaxation times and can therefore be distinguished using MRI. So this is the advantage of magnetic. So you can, if the cancer is in different tissues or different organs, then you will have to play with the relaxation modes of these magnetic nanoparticles and application of external magnetic force to find out how effectively the technology can be used to treat the cancer and eliminate the cancer cells. So static MR measurements is another quartz tube filled with ferrofluids, and then they try to find out direct measurements of ferrofluids susceptible agree well with the value extracted from MRI studies, and then you can get the more information about the properties of ferrofluids or magnetic nanoparticles inside the body. So as magnetic nanoparticles respond to external magnetic field gradient, it may be possible to magnetically tag certain objects and then extract these from a flowing mixture using magnetic fields. One advantage of this approach is compared to other separation methods is that external magnetic field can be turned on and off, and allowing the separation between tagged and untagged objects to be well controlled. Also important to understand the magnetohydrodynamics for this application. So, for our present thing, you just have to understand the theory of this, but not because some of these things are still in experimental status. So it's interesting to know what are the changes happening there. Applications of magnetic nanoparticles in biomedicine. This is a very good review published in 2003, still very useful for us. So you use the magnet here, external magnet getting, and then the drug is released in the system. So using magnetic nanoparticle to trigger controlled drug release system is because of the magnetic nanoparticles show a large response to magnetic field. They can be used to trigger reactions simply by using external fields. And in such scenario, you use some dendrimers, or PNI, PAM is a thermosensitive polymer, polyacrylamide, and its temperature responsive polymer, known as it is critical solution temperature is 32 degrees centigrade, which has a significant volume collapse near 40 degrees centigrade. So now you are combining the properties of the polymer and properties of the magnetic hyperthermia and getting the drug released from the polymeric nanoparticles, magnetic nanoparticles, and that is where this PNI PAM is utilized, and we'll see more on about this in dendrimers class. The resulting composite can be heating using external magnetic field, which is in turn can trigger the volume change, and this phenomenon can be exploited for controlled drug release system. So you can control the drug release because of the external excitation. You can put little bit of magnetic field and then stop there, and then again put again and then stop. So you can have a controlled release of the drug through these dendrimer polymers, PMI, PAM matrix. So TEM images of nanoparticles, TEM images of nanoparticle attached with PNMI is shown here, and it is almost 200 nanometers. So you can see these are very small particles, and this may degrade the controlled response as only portion of PNI PAM is targeted. So drug release in PNI PM is use dendrimer and ferrofluid composites, and drug release rate from magnetically heated PNI PAM ferric oxide composite is much higher than this release professor. So this is the normal ferrofluid, and this is the combination composite of PNI PM, and you can see the drug release much simple PNI PAM and then combination of that. So you can see the significant difference in the drug release system in these things. So conclusions are, in addition to being small compared to most biological structures, magnetic nanoparticles have distinctly different magnetic properties from bulk materials, making them potentially very attractive for biomedical applications. Magnetic nanoparticles have direct applications in medicine, including magnetic hyperthermia and MRI contrast agents, but can also introduce new functionalities when combined with other materials such as targeted drug delivery and controlled drug release. One of the central ideas of magnetic nanoparticles applications is the ability to manipulate the particles using an external magnetic field, and there is still a great deal of work to be done on understanding how magnetic nanoparticles interact with the body, toxicity, excreting the nanoparticles, and so on. So these are additional resources. I will recommend you to read them. They are available online, and you can read those papers. So thank you very much. And we studied in this class quantum dots, semiconductor, and magnetic nanoparticles, their biomedical applications. If you have any questions, please email me and I will try to respond you back. Take care, all the best, and have a great day.